My name's Bo. I work for Brightcove. Actually, I work for Yuri Resnick's team. Seems like my screen's shaking. I don't know why. Today I'm going to talk about work called low latency dash streaming demo using open source tools. About myself, I'm working at Brightcove Video Research Team as a video system engineer. I started here since July 2019. I do research mainly in video delivery, video playback, and CDN. So a little context about my talk. So in this March, the DASH Industry Forum, DASH IF, published a new change request to the DASH IOP guidelines on low latency mode for DASH, LDASH. It is based on the earlier work on DVB low latency DASH. It proposes several important new features such as resync elements, service description, and also FFmpeg recently added support for these latest changes. So at Brightcove, we have experimented with different open source tools to build a very simple LDASH server. We use FFmpeg and GPAC software called Node GPAC Dash. We added minimum integration code and minimum modification to the existing tools. So in this presentation, we will present our implementation of this video server, and we will show a quick demo at the end of the presentation. So our full report can be found here in this link. So first of all, what is low latency? So a low latency stream must have a glass-to-glass latency of around 5 seconds. I mean, from the encoder screen to the player screen. So a low latency dash server uses chunked video encoding to push the segment chunk by chunk to players. So video segments are divided into smaller chunks. So on this diagram on the right-hand side, this is a diagram made by Will Law from Akamai. It shows the structure of one CMAF low latency CMAF segment. So the segments is divided into a sequence of smaller chunks. Each chunk is basically a pair of MOF box and MDAT box. Given that the client and the server, low latency client and the server are fully synchronized, a player will request the video segment, the latest video segment on the live edge as soon as the first chunk becomes available. So no additional buffering is allowed. So when the server receives or CDN receives the request for segment, it will push the segment to the client chunk by chunk when it's been generated using HTTP 1.1 chunked transfer encoding (CTE). So the server also needs to set the availability time offset in the MPD, dash MPD, to adjust the segment availability time to make it available early for clients to download. So the latest changes proposed by Dash IF include several new features. First one is the resync element. It contains a list of resync points which a stream can be accessed independently. A resync element allows fast stream joining. A resync point contains at least the following four fields. The first one is a byte offset, earliest presentation time, the stream access point type, and also a marker field indicating whether the resync point can be detected using in-band or out-band information. And the proposal also add several new service description fields to inform how the player should operate under a low latency mode. This includes, for example, the target maximum and minimum latency values. So it also recommends a few recommended settings for the server and client. For example, the target server to client latency should be around 3.5 seconds. The chunk duration should be 500 milliseconds. And also LDASH allows event messages, e-message, to be inserted in the middle of a segment. This would allow faster delivery of events to the client. Previously, we know that e-message can only be inserted in the beginning of a segment. So previously at Brightcove, we have evaluated different low latency technologies. First one is DVB low latency dash. It is a GPAC using GPAC software, GPAC low latency dash implementation. Basically, no GPAC dash, dashcast, MP4 clients. We also evaluated Apple's low latency HOS using Apple's reference server and also the iOS AV player. We also evaluated community-driven low latency HOS using AWS IVS service and the sample player provided by them. So in this work, we're going to show low latency dash implementation demo. So this is the demo setup. So we split our implementation, our setup in two different geographic locations. We have the encoder and player running in Boston area, and we have the server software running in Seattle area. So in Boston, we have the OBS studio acting as the live encoder, capturing the video on my side, and then stream it over to the server using RTMP. And then in Seattle, the FFmpeg received the RTMP stream, converted into LDASH format, and then writes the manifest and the segments into local disk. So we also run Node GPAC Dash, which is a Node.js software, which handles the client request from the players in Boston. And then when it receives a client request, it fetches the segments chunk by chunk from disk and then send it over to the player over the internet. So given this setup, we have a coast-to-coast round-trip delay from US East Coast to West Coast. So this is the live video encoding in OBS. The video bitrate is 2500 kbps. Encoder is X264. We use a very fast preset. Resolution is 800 by 600. Frame rate is 30 FPS. Keyframe interval is 120 frames. So given a frame rate of 30 FPS, the segment duration is 4 seconds. And what follows is the RTMP ingest stream for the OBS and FFmpeg. We also burn the timestamp, the current timestamp, into the video. This is used for latency evaluation. So this is the FFmpeg command to run the low latency dash server. So FFmpeg ingested RTMP stream from OBS and outputs the content, LDASH content, to the local disk. And this is the command. We highlight 3 options, command line options. The first one is the LDASH. It signals the use of low latency dash mode. And we also need to set streaming. So this is used to signal chunked streaming mode. And also LDASH require segment template. So we cannot use segment timeline. Template must be used. So that needs to be set in the command line option. Next one is the chunked video server. We use this to handle the client chunked segment request and deliver video segment using HTTP 1.1 CTE. So initially we planned to develop our own chunk video server, but we found this Node GPAC Dash, the GPAC software. It meets most of the needs, the features that we need. So we ended up modifying the existing tool. So Node GPAC Dash was developed for DVB low latency dash back to 2015 around. It implements a chunked video server, has most of the features that we need. However, there is one problem. it uses a EODS box to identify the end of the segment. So we know that for HTTP 1.1 chunk transfer, we have to send a zero length chunk to the client at the end of the transfer to signal the end of the transfer. So no GPAC dash use EODS box. It is only used by GPAC software. It is not supported by FFmpeg. So in order to integrate FFmpeg with no GPAC dash, we need another way to detect the segment end in order to end the transfer. So we modified this no GPAC dash to make it working with FFmpeg. The source code is available here. So, excuse me. So this is the state machine for the chunked video transfer. So instead of I'm not going to walk through this diagram. So instead of using EODS box, we use the to signal the segment end. We use the segment file renaming to detect the segment end. So we notice that FFmpeg, when it write in progress segment chunk by chunk to disk, the segment name, the file name is has a temp extension. So when the segment finish, FFmpeg rename that file to .m4s. So when it completes, so this can be used to detect the segment end when the file renaming happens. So when this happens, we send a zero length chunk to the player, so the player can stop receiving that segment. So there must be some better method to do this. However, the specification does not define the way to do that. So if you guys know a better way to do this, please let me know. Yeah, I can modify my implementation. So this is a LDASH MPD generated by FFmpeg. As we can see, it sets the availability time offset. The value equals to the segment duration minus the chunk duration. So we have a 4-second segment duration, and each video frame is one chunk. So 4 minus the frame duration gives the availability time offset, and we also need to set the availability time completes to false. So finally, in the demo, we have the LDASH playback. We use the latest Dash.js player. We need to turn on the low latency mode. We also need to synchronize the server with the player. For example, on Linux server, we run NTPD to synchronize the server with the standard time. Also, Dash.js automatically synchronize with Akamai time server, so we don't need to do anything for Dash.js. So this is the URL we play using Dash.js. It runs on port 8080. And also we need to obtain the current time from time.is. We then compare the time difference between the embedded timestamp in the video and also the current time from time.is, and this gives the glass-to-glass latency. So for our coast-to-coast round-trip setup, we observed around 6-second glass-to-glass latency, but Dash.js only report a latency of only 3 seconds. This is from the server CDN to the client, so this is not bad. So, but that also means the live encoding in OBS and RTMP transfer took about 3 seconds, which is a lot. So we may need to reduce this latency by using a faster encoder. We can also use real-time streaming protocols such as SRT or WebRTC for ingest. Previously, we have evaluated AWS IVS, the community-driven low-latency HOS. we measured about 6-second glass-to-glass latency. But the AWS, they have the server and CDN all around the country, so they are much closer to our player in Boston than from Seattle. So I'll show a demo here. I'll open my terminal. First of all, I'll start FFmpeg. I'll start the Node GPAC.
Oh, sorry to interrupt, but
Sure.
we're not seeing your terminal.
Oh, sorry. Okay. Forgot to share that.
And also, while Bo's doing that, if people have questions, if they want to use the raise hand button, then it'll be easier to know that you have a question, or just type it into the chat if you'd rather do that.
Okay. Yeah, I see some message. Okay. Fine. Okay, great. So I'll share my let's see the terminal. Where's my terminal? Here. Okay. Fine. Do you see my terminal?
No. Sorry. No. Oh, hang on. Something's happening.
Okay. Yeah.
Okay. Now we see it.
Okay, great. So this is the FFmpeg. This server, it does not run in. So the previous lab was running the server in Seattle in one of our server at Brightcove. But since our server is under some problems, so we moved the servers to AWS. It runs in Oregon, the US West 2 zone. So this is FFmpeg. This is AWS. This is a free tier instance. This is Node GPAC Dash, runs on the same server. Both are running. So OBS. I'll start streaming. So in a short while, we see FFmpeg started to ingest and dumping segments to disk. Next thing is to play the stream. So here I need to turn on low latency mode in Dash.js. Click load. So the video will start in a few seconds.
But yeah,
Yeah.
Now we see it. It's been just frozen screen for a while,
Right,
but now
right.
we see it.
Right. So we see the latency. This is time.is. Latency is about 5 seconds. It's now it's increasing for some reason. I don't know why. It was 5 seconds when I just opened the video. So it's now 7 seconds. So that could be some extra delay. And I think this is wrong. This value is wrong in Dash.js because on the screen we can see the difference of the timestamp is 7 seconds right now, but I don't know why Dash.js report a live latency of almost 14 seconds. So this value is wrong. Latency is 6 or 7 seconds.
But can you share the other window where you see those 6-7 seconds? Because right now we only see.
You don't see the browser, right? Sorry.
Yeah, sorry, I'm just seeing the terminal.
Okay. Yeah, okay. I think I'll share my entire screen in this case.
That's probably good. And then I think Matt had a question.
Okay.
Or a comment.
Sure. Go ahead.
Yeah, just wondering if any of that unanticipated latency came down to RTMP.
Yeah, RTMP takes about 3 seconds to ingest from East Coast to West Coast.
Right. I just meant the variability in your tests. I just kind of, if I had to start investigating, I'd look at the RTMP link first. But
yeah,
that's a good point. That protocol doesn't guarantee any latencies whatsoever. You're really up to, whatever is going to happen.
That's true. That's true. Yeah, but OBS, they don't support WebRTC. If I'll choose another protocol, I'll choose WebRTC or HRT. So
Okay. Okay.
Yeah.
Book. Can we see your screen with demo?
Okay. Yeah, that's right. So now let's switch to the demo. So the latency now is about 8 seconds. It's increasing. Right. Let me do it again. This is my OBS. Yeah, start it again. Latency is 5 seconds, 6 seconds initially, but the you see the 31, 24, 25 on the player, it's 6 or 7 seconds earlier. So that gives the difference gives the latency. But on the DASH.js player, I don't know why it reports 15 seconds. So this must be wrong. Yeah, I trust my eyes. Yeah, this is a bug in the player, I think. Yeah, today is the first time I see this high value. Before today, I always see like 3 seconds. Yeah, maybe I'm streaming from AWS, and that's why.
Or maybe there is difference in timing on machines, so could be many other reasons.
Yeah, DASH.js is synchronized with the Akamai time server, unless Akamai time server is wrong. That's also a possibility, right?
But the good news is that FFmpeg seems working, and we see you streaming with low latency Dash protocol.
Right.
Okay.
Right. Okay. So at the end, I'm going to discuss several potential issues with low latency Dash. First of all, in general, the low latency streaming, it has a scalability issue. It's less scalable than regular latency due to chunked segment transfer, because we need to keep the TCP connection open until the chunked transfer complete. And that's a big burden to the server and factor the scalability. And also, we see a trade-off between the chunk size and also the latency. So that's because a smaller chunk size, given a smaller chunk size, we can achieve lower latency. But we have to frequently writing the little smaller chunks to disk or transfer it over network. That causes a high I/O overhead. And if we have a larger chunk size, the latency is higher, but the I/O overhead is lower. This is a trade-off we need to deal with. And also, HTTP version for low latency Dash is another problem. Currently, low latency Dash only supports HTTP 1.1, but we know that HTTP 2 and 3 can bring a lot of benefits to web video streaming potentially. So in order to take advantage of this higher HTTP version, low latency Dash needs to support these protocols, HTTP protocols. And also, there is a stability issue with low latency Dash. When the player plays too close to the stream live edge, there could be lots of uncertainties. For example, the client and the server can lose synchronization due to clock drift, and we can also have spikes in the system resource usage that could delay the output of segments. And this happens particularly to cloud-based deployments when the ingest and delivery happens over public internet. And the result is that the client may request segments that are not generated. So the server in this case will return 404 not found, and the playback may stall as a result. And also, ad insertion could be hard with low latency. That's because due to the high turnaround time at the ad decision server, so it takes a long time to get the feedback decision from ad server, but we only have 2-3 seconds from the live ad, so the time is very tight for targeted ad. Also, another competing technology is low latency HOS. They share a very similar idea, but looks like low latency dash is simpler and maybe more efficient. The disadvantage with low latency dash, as I mentioned, it is less stable than low latency HOS. That's the end of my talk. Any questions?
That's awesome. Thank you both. Actually, I have one question on the ad insertion. So what ways to mitigate that, I guess, ad server latency could possibly exist to do targeted advertising? And I think, Matt, you might have some thoughts there, because I saw you nodding your head as Bo was talking about that topic.
Yeah, I can't hit enter in Teams. It's not letting me submit my suggestion, which is you run 2 player instances, you pre-buffer the ad, you flip the player, and then you transition back to your main content. Because otherwise, no one wants to see the buffering or delay and wait for an ad. That's one of the things we did with our Amazon video players.
I see. That's a good idea, I think.
Well, let me kind of add that, if you're dealing with existing ad-based workflows, which majority of them have been built on the concepts of manifest manipulations, where there is existing streams, and you just replace segments in this, include discontinuities in case of HLS, or a new period in case of DASH. Well, this low latency model kind of breaks it. You need to operate not at the granularity of segments, or you need to deal with subsegments. There is a state of transfers that needs to be accounted for, so it becomes much more complicated. What Bo presented generally is kind of baby steps towards understanding of the scalability issues, the stability of this types of technologies, and how close it is to the market in terms of where open source community is right now implementing some of these concepts. And what we're seeing is that it's actually moving along quite well, and we can run something, we can see some demos, but certainly there is more space for improvements just going in the future. It seems pretty complex topic. Just my observation.
Right. So in the latest spec, they allowed insertion of e-message in the middle of the segment, so that would allow faster delivery of signaling of the ad content. I mean, like expiration of the current MPD in case of DASH, and start a new period for the ad.
Yeah, but then the expectation is that all players will support messages, which of course is not.
That's true.
It's not gonna happen overnight. So it's
yeah, they have to player and server needs to implement it. It's only a proposal. Yeah.
Yep.
Looks like Andy has a question.
Well, the answer that Yuri provided has my full attention. You're concerned about broad player support, broad client support, broad smart TV support. Did you say A messages? You mean E message? I didn't hear.
Event message.
Okay, does that mean that you are of the gang who says that these not just start the ad here, but this is the ad ID, and all these other messages belong in the e-message boxes in band and don't belong in the manifest file, because goodness knows some of my best friends and some of yours, especially Rufel at Unified Streaming, doesn't like having all this clutter getting into the e-message box streams. And since he's pushing the DVB in a more formal direction, doesn't all the ID and signaling belong in the MPD? And if not, why not? And how do we deal with the fact that it winds up in 2 or 3 places at once?
You mean the move all the signaling, add signaling to MPD?
Well, I think
the universal ad ID belongs as a manifest event.
Well, look, there are 2 school of thoughts here. So if you look at what smooth streaming was doing and what ultraviolet was doing, they were pushing everything through MPDs embedded in streams. I'm sorry, they were pushing everything through messages embedded in streams. And in fact, one of the messages embedded in streams could be carrying MPD update. So you could signal a whole new manifest by sending it within the stream. Well, that's one school of thought. The other school of thought is, well, you do everything through manifests. And you could design a system either way. The question is on which, end of the spectrum your current implementation is. I guess that's really the question.
Right. Right. Actually, I think the for low latency dash, the MPD is usually not updated, and we use event message to expire the current MPD and start a new MPD and add a new period.